said, we have Ilya, who's going to give a short talk on his topic. And then right after that, it's not a short talk, it's a full talk. By short, I meant like not hours. So it's a full talk by Ilya, which obviously Ilya doesn't need any introduction but someone who might not know, Ilya is the maintainer for the OVS, and we really appreciate his efforts. He's been pretty much carrying the maintainership burden on his shoulders. We appreciate it a lot. And right after Ilya's talk, I have a request after the questions. We are all set for the photo. So, and photo is very important these days. So my request is that if we could just make our way out from one of these entrances, and the photo is going to be right there. We have picked a very good spot with sun and shade, and allegedly there's going to be a drone taking a photo also. So let's figure all of this out. This is high tech, man, high tech. So with that said, Ilya, all yours.
Hi. Hello everyone. I'm Ilya Maximets. I'm working mostly on OVS and OVSDB for last maybe a year or so. And today's talk is about OVSDB performance updates for last year and some updates for ovn-heater and what's changed and how to basically use the data that it provides in the performance and scale environment. Okay. The first slide was just to take a brief look on the overall OVN architecture. I'm just reusing it from the last year. What we have in OVN is a few central components like northbound database, OVN NordD, and southbound database, and a bunch of nodes or hypervisors. On each hypervisor, we have an OVN controller, which is controlling local OVS vSwitch and programming flows. And each OVN controller is subscribed to all the updates from the southbound database. And NordD is processing data created by users, by CMS, or humans, translating it into the representation that OVN controllers can understand and use programming flows on each host. Here's some recap of the work done in the last year, 2021 presentation on a similar topic. We had a lot of performance improvements, basically mostly focused on transaction performance and monitored performance. We changed database file format into 15. We applied a lot of algorithmic changes to manipulations with large sets in the database implementation. We deduplicated objects in memory to save time and also memory. And it resulted in significant performance improvements and all of that is now part of OVS 217. So what's next? Do we actually need more performance? That's the question. Well, sure, more performance is always better, right? Everyone will tell you that more performance is always better. On the other hand, OVSDB didn't show up as a performance bottleneck throughout the last year since we adopted all the changes implemented for OVS 217. And that's an interesting point. Of course, there are some things that we need to remember. There are some cases where control plane like CMS or OVN itself is not using database efficiently. And in these cases, it's possible to bloat out the database to the point of failure. It's inevitable. Every database will fail at some point, as long as you add continuously data to it. And because we just don't have infinite resources. But what this statement means is that at the point of failure, it's usually other components are already suffering in the system. So it's not OVSDB server, which is a bottleneck that's keeping everyone back. So that's a good follow-up from like last year's presentation. So this is kind of a result of it. So focus this year is improving performance in corner cases, which can destabilize the database at large scale, chasing anomalies, and improving general stability. And there are some general performance improvements as well, as it's cut off on the slide, but we'll get to that. So what I was using it for testing. Last year I was using basically synthetic tests focused on transaction performance and monitoring performance for just the OVSDB server process. This year, since we are talking more about general stability and corner cases for cluster setups, we should use closer to real-world setup, which is in our case ovn-heater. So what is ovn-heater is a testing tool which is designed to mimic some CMSs, mainly OVN Kubernetes, and it's working on top of pure OVN setup. So under the hood, we have OVN fake multi-node, which can deploy multiple fake nodes on a single physical machine, and we can expand this to multiple physical machines to deploy large-scale clusters having limited amount of hardware resources. Since we don't really have any overhead for like full Kubernetes or full OpenStack, we can pack a lot more of these fake nodes on the single node, on a single physical server, and test performance of the OVN, particularly without taking much time looking at performance of other components that can influence our test. And yeah, ovn-heater collects a lot of data from the test, compares, collects the results, and plots some nice charts for us that we can use for performance analysis at scale. So the test scenario for this setup, those slides are a little bit full. I don't know. That's better. The scenario for this setup is 250 fake nodes in ovn-heater deployment with about 13,000 logical ports, so 55 pods per node kind of situation for OVN Kubernetes analogy, and about 16,000 load balancers, which with 2 backends each, which translates roughly to 5,000 something OVN Kubernetes services in this case. In our configuration, we are using a cluster database, RAF with free servers, and OVN monitor role is enabled, but we will not show any charts for conditional monitoring on this presentation, but in general, the data is not very different for this test scenario. Here are the first chart that generated by ovn-heater. This is a CPU usage chart for the test using OVS-217 and OVN-2206. It's important that we are always getting them in pairs because OVN is using databases very differently depending on the version, and OVS is also evolving. What we can see here is we can clearly see phases of the ovn-heater test. The first of the 4 parts is the base cluster bring up, is when we are deploying our 250 fake nodes. And we see CPU usage is growing linearly for this phase as we're adding more nodes. It's mostly an OVN inefficiency, as every time we add a new node, OVN basically rewrites the whole southbound database due to changes in data path groups. This can be avoided. We are not focusing today on this part, as it's not a very common operation in the cluster. It's also doesn't use 100% of our CPU here, so it's kind of okay. The next step is ovn-heater adding all the ports to the cluster, almost all the ports to the cluster. And here we have some CPU usage close to about 15%, I guess. Next step is adding all the load balancers to the cluster. And here we have some significant CPU usage. The first spike you can see here is most likely due to allocation of a lot of new resources when we first add the first load balancer and other stuff. But then it like stabilizes and stays at about 40%. And the last step is an actual test in the ovn-heater. And this is a mixed workload where we adding ports, adding load balancers, and also checking if the connectivity between all these fake nodes and pods that we created. And using ping in this case. And we see that the load is similar to what we had while adding load balancers. So it's about 40%, sometimes lower, sometimes slightly higher. And the next slide is here just to say why we're not talking about northbound database today. This is the same chart, but for northbound database, CPU usage is basically about 2 to 5%, maybe even lower. Let's go back a little quick. One thing not addressed on this slide is high 100% spikes. And what it is the database compactions. This is what we will talk about next. What's a database compaction? So you probably know that database files are incremental in OVSDB, and each new change is a new record in this database file. We have some initial snapshot and a lot of incremental updates. This works good for performance reasons because you don't need to do random writes or have special structure of the file. But the file grows out of bound and you need to create a new base snapshot at some point in order to keep it at some reasonable size. Perhaps a few problems with that. First is, and the main problem is that database is not responsive at the moment while it creates the database snapshot. You can see here on the slide, it's a part of the log reporting how long the database compaction took. In this case, it was like 8 seconds, where 7 seconds was just creating this new data structures in memory, and about 1 second writing them on disk. The issue is partially solved by, well, partially solved by transferring the leadership in the Raft cluster. What it does is, so the clients are notified about the leader change, and write-heavy clients like ovn-heater can reconnect to a new leader and continue operation without much interruption. There were a lot of issues with that. We caught a lot of bugs in different parts of Raft and also software which is using OVSDB server, like OVN Kubernetes and OpenStack Neutron plugins. So there is a problem though, because OVN controllers do not really reconnect because they are not write-heavy clients and they don't need to reconnect and they do not reconnect. It means that if we have a 3-node Raft cluster, 1/3 of a cluster will not receive updates for the network for this, in this case, 8 seconds, which is not great. What's the solution? Well, if you ask anyone, then they will tell you just to run it in a different thread, right? The first thing that comes to mind. Well, my personal opinion on this is throwing more cores on the task is most, I think, is the last thing that you should do. Only if you don't have a choice. In many other cases, you may just perform some, you just write better code or use a better architecture. A few issues with having a thread is that internal data structures in OVSDB server are not thread safe because OVSDB server is initially a single-threaded application. And if we want to continue modifying the database while we're creating a snapshot, we need to somehow accommodate that. So the solution is copy on write. And yeah, maybe one step back, why we're going with this solution anyway, is because if you look at this database sizes, it grows up to hundreds of megabytes, and it can be 500 megabytes, and just writing that or creating that structure takes a lot of time. Like you just think about it, it's really hard to optimize it for sub-second times. So either we completely rework everything and employ some different architecture, or we moving this to a different thread. So here's some example of how a database row is looking in the memory. We have an array of columns. Each column is a datum object, which has a pointer to keys and values and the number of keys and values in this column. What we can do is the simplest solution how to implement the copy and write here is add a reference counter. And basically just copy the pointers instead of, and increase the reference counter instead of copying the whole structure every time. This way we can, what we can do with that is we can quickly create a shallow copy of the whole database in the main thread. Then give it to a compaction thread that will transform it into the database file format for us. And then the main thread can get this result and write it on disk. While it's happening, the main thread may process new transactions, and every time the main thread needs to modify the data, it will copy it. We conveniently have a Raft log that stores all the changes. And if we remember where we started our compaction, we know what incremental changes we made on top. So when we are writing in the file, we can write a new snapshot and then write on top all the changes that happened while we were creating this snapshot. And there are a few bonuses. We also, while doing that, copy and write is actually very performance beneficial. Database is doing a lot of memory copies during the normal operation. Now they are all almost free. As we are usually copying data and not modifying it, we can save a lot of CPU time on this kind of operations, up to 40% on row transformations. Not a general 40%, but 40% of what we already have. So this is another copy from the log file with a compaction thread. You can see it's a debug log because compactions left under 1 second are not logged. So has to enable debug logging for this as it's working fast. We have only a few hundred milliseconds on the main thread, and most of the work is done in the compaction thread that took about 5 seconds, creating new data structures. Actual shallow copy is init phase, which is under 200 milliseconds, and the write on disk is a bit heavier, like 400 milliseconds. And yeah, we also have some other notable performance optimizations in OVS 3.0. Besides the database compaction thread, it's improvement of performance of Json parser. As you know, OVSDB server is using Json for database storage, for network transfers of updates and transactions, and it was improved up to 40% for JSON strings. It's work of Rosemary. We also have a new flag for ideal clients from Dumitru to allow not to send all the not changed columns for NORD process. And we're now using a faster SHE1 implementation from OpenSSL library, which is used for error detections in the file. And here are some results. This is OVS 3.0 with the same OVN2206. You can see some, I left the 40% that we had before and the 30% which is now. And the mixed workload is also much lower in CPU usage. Here are both graphs on the side by side. I'm not sure if it's usable, but you can see that, yeah, overall performance improvement is noticeable. But so far we talked about CPU usage. Now we need to take a look at the other chart that ovn-heater is producing, and this is the memory consumption. The elephant in the room, we can see that this is the point where we're starting to add load balancers, and memory jumps like 7 gigabytes at once, which is not great. Running the same test on the under Valgrind, we can notice that almost all of that memory is copying weak references into the transaction history. So what the transaction history is allowing fast resynchronization of data when the client reconnects, but it's not used for reference counting or for data integrity. So we just don't need this data in the transaction history. We don't need to store weak reference objects, references between rows in the transaction history. So we may just not store it. That's a simple solution. Alternative solution is to employ data path groups for southbound load balancers in OVN, basically changing the schema. And this way, basically all of that lists of data paths were taking about 70% of the database, and this was just repeated UUIDs of the same data paths taking hundreds of megabytes. Changing that, we significantly reduced database size, which also helps. So we should use both solutions, right? They are both beneficial and should be used. And here's what we have after applying both changes for OVS 3.0 and OVN 2209. We have now only 670 megabytes instead of 7.3 gigabytes of memory. And actually, recently, Han Zhou also found a bug in one of the previous patches of mine, and this value should be 100 megabytes lower. And here's a CPU usage graph when we applied both solutions. So because we now not copying all the weak references and not having so huge database, our CPU usage has actually dropped down to 5% on the southbound side. We also have some relay updates. We added transaction history support and improved performance of column mutations. There are some bug fixes in the raft. I will not go any deep because I'm out of time. And the ability to log changes in particular tables created by Dimitri, which is very beneficial for if you want to know when exactly some tables are updated. Yeah, that's all from my side. Thanks.
Thank you very much, Ilya. Computer Science 101 is you can shrink the memory size and then the CPU computation will go up, or you have CPU less and more memories needed. I would like to recognize all the people in the community and in other places who worked tirelessly in the last 18 months to improve the OVN's performance tremendously. They found bottlenecks, they eliminated them, no regressions, etc. Chris Wright touched on it a little bit also, and now we have live traffic going in telcos on OVN. So huge transformation. This was one snippet or one sliver of all the work that Ilya presented, but behind that, there is like ages and ages of work and some of the best engineering work that I've seen in a very long time. So thank you very much for everybody who worked on it. Are there questions? Yes, sir.
What about OVSDB relay? Do you see a use case for it still, now that OVSDB server is so performant?
For us, I think so, yes. For us, still use cases. Basically, if you want to scale higher, you will need a relay at some point, just because you have limited network connectivity to your servers. So basically, the scenario for relay, in my opinion, is more of a CDN. So if you have only 3 servers which are serving all the monitors, they need to send a lot of data to all these monitors. And you can be limited by your network performance at some point. And yeah, it's also not reasonable to run tens of thousands, maybe, clients on the same database.
Thanks. Wendy.
Yeah, I do have some questions about the details. I think in one slide you said that I think the Rosemary, right, a Json parser, and with that, I mean the performance improved about 40%. Just out of curiosity, how did you improve the Json parser, or what do you do differently compared to before?
Okay, yeah. So OVS has a JSON library in its own, and implementations, of course, for a parser to parse from string to the JSON structure internals and back. So what are the main bits of this were basically low-level optimizations, like reading large chunks at once, not reading like one character after another and comparing, finding better branch prediction, restructuring the code for better execution flow. So not jump too much, cache locality, and this kind of optimizations.
Okay, I see. Yeah, thank you.
Hi, Ilya. We have a question for you online. So Robert Acosta says, first of all, he wants to congratulate you on your work. He asks, is there any issue related to the alternative memory allocation libraries, such as Gemlock, that does not allow it to be incorporated by default, since the performance test results are superior to the standard libc?
Yeah, it's a good question. So what we noticed trying to run different tests with ovn-heater with databases is that glibc memory allocator is not very stable in its performance, and it consumes way more memory than it should, and it also doesn't bring it back to the system. For example, we had to employ memory trim calls every time after the database compaction, because when we're creating the new database snapshot, our memory usage grows twice as much, and then it doesn't go back, because glibc just doesn't free that memory back to the system. Basically never frees it. It's a known issue of glibc. It doesn't free fast bins that it's using, and we are allocating a lot of small objects, even if we are freeing them, glibc doesn't give them back to the system. So when we use gmalloc, it shows much better performance, maybe even 40% performance we can save by just running with gmalloc instead of glibc-based allocator. I don't see any issues with integrating it by default. I think it's only main issues are management decisions of willingness of people to maintain a package of a different memory allocator in the system. Because as far as I know, not every distribution is packaging gmalloc by default, and it's maybe a burden, and some additional testing is required, of course. But I don't see any reason why not.
Thank you very much. Thank you very much, everybody. Thank you, Ilya. Appreciate it.